Okay, sorry for the 20-second delay in the start of class. I was having technical difficulties, and they are over. I did the old, you've seen the IT guys, turn it off, you try to turn it off and back on again, and I did, and it worked. So, anyways, so how are we doing so far? Anybody have any questions about anything before we start? So we're in my very favorite topic of thermodynamics, which I'm so excited to be here and talk to you about today. What we've covered so far is the first law of thermodynamics. And the first law is the change of internal energy for a system is its work plus heat, where the internal energy is path independent, but the work and heat are path dependent. And then we have our system here. Energy flowing into the system is in the positive direction. Energy flowing out of the system is in the negative direction. So this is going to become important in the next example. And we already did an example of heat transfer is the heat capacity times the change in temperature, or the mass times the specific heat capacity times the change in temperature. Okay, so we're going to do that for this problem here. And so this problem here, we have a 32.5 gram cube of aluminum at 45.8 degrees Celsius submerged into 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? Assume that there's no heat transfer other than the aluminum and the water. Okay, so the idea here is, and here's my beautiful Picasso-worthy picture of a aluminum cube in water. And I have that red arrow coming out showing that the heat is flowing out of the cube and into the water. So that's the idea is that the heat loss of the aluminum equals the heat gained by the water. So the heat loss of the aluminum, so it's in negative direction, minus mass aluminum CS aluminum, and the delta T delta T is always T final minus T initial for both for the aluminum. So maybe I should minus Q AL equals Q. I'm gonna call it H2O takes too long. I'm gonna call water W. So heat transfer water. So then this is the mass of the water, specific heat capacity of the water, final water minus T initial water. Okay, so one thing to note though is that the final temperature is the same for both. So I'm just gonna get rid of the subscripts there because it's going to take too long to write all that. So final temperature is the same for both. Actually, maybe I'll keep it on there. I'll drop it in the future ones. So now we got to solve for TF. It's getting me an algebra nightmare. Okay. So let me make sure that this is 6.3. I want to make sure I put the negative sign in the right spot. 6.3. Oh yeah, they're the same thing. I put the negative sign on the other side, but oh well. I'm looking at the books the way they did this example right now, and they put all the numbers in. I like to do the algebra first, and then do the numbers last. That's my own personal preference. So however you want to solve it. So either way, we need to get the TFs all on the same side. So let me FOIL this. So I'll go over here. minus mass. I was A for aluminum, specific heat capacity, aluminum, temperature minus Ti aluminum. Oh, I already wrote that, shoot. Oh, well, that's fine. It's foiling it. Okay, so I'll foil it plus. I can copy this. So people have nightmares about doing math in front of people. Okay. What I've done here, I just foiled it. Multiplied this through, so this to both those terms. The negative becomes a positive. And then we get mass of water, heat capacity of water, temperature minus mass of water, heat capacity of water, initial water. Okay. So now we got to get the temperatures on the same side. So we add that side there, and we subtract this one over here. So this one is going to go on this side, and this one here is going to go on that side. So we are going to say mass of aluminum, heat capacity aluminum, temperature initial aluminum, equals mass of water, heat capacity of water, final temperature, plus masses of aluminum, heat capacity aluminum, final temperature, and then we're going to take this term. Well, I guess I'll put it. This says minus mass of water, heat capacity of water, to initial water. I'm going to move this term over here. Okay, so of course it becomes positive, and I have to erase it. Do you understand what I'm doing there? Now the next step is, that stays the same. I have to pull out the temperature, final temperature, mass of water, heat capacity of water, plus mass of aluminum, heat capacity of aluminum. And let's go ahead and copy, come on, copy you. That's still there. And now I just have to take this term and then take this term and divide it. So temperature is that, and then divide this term. So if you like putting the numbers in, I like doing the algebra first. That's my own personal preference. But if you like throwing the numbers in like the book does it, that's fine. So then you put in the terms. I can't read that up there. Mass of the aluminum. Actually, I need more room. Temperature is mass of the aluminum, 32.5 grams aluminum. Heat capacity of aluminum. I don't know the heat capacity of aluminum. Heat capacity of aluminum is 0.903. That's a 9. Joules per gram degree Celsius. Initial temperature of aluminum, 45.8 degrees Celsius. Plus mass of water, 105.3. water, the space here. Heat capacity 4.18 joules per gram degree Celsius. That's the heat capacity of water. Temperature initial 15.4 degrees Celsius. All over mass of water, heat capacity of water 105.3 grams water times 4.18 joules per gram degree Celsius plus the mass of the aluminum, 32.5 grams aluminum, heat capacity of aluminum 0.903 joules per gram degree Celsius. Okay. So then you got to put this in your calculator. This is pretty complicated. I can see why the book put the numbers in first. Man, now my phone doesn't recognize my fingerprint. This is a fun day. Hopefully your brains are working better than my electronics. 32.5 times, I guess I did do the whole quantity. 903 times 45.8 plus 105.3 times 4.18 times 15.4, and that divided by the quantity 0.5 times 4.18 plus 32.5 times 0.903. And I'm getting 17.3 equals 17.3 degrees Celsius. Okay. So let me take a picture. That's not really a hard problem other than the fact that it's lots of bookkeeping. Okay, so let's talk about units. Unit-wise, grams of aluminum cancel, degrees Celsius cancel there. Same thing for, I'll do green for water. Grams cancel there, degrees Celsius cancel there. And then down here at the bottom, grams cancel there. And grams cancel there. And you can also see, I'll do purple, joules cancels in all of them. And dimension-wise, we're at 1 over 1 divided by degrees Celsius, which is degrees Celsius. So those are the terms there. So recap for this one. We have a hot cube of metal that we threw into water, cooler water, and we want to know what the final temperature is. So the idea here, assuming it's thermally isolated, that's also known as adiabatic. If you heard the term adiabatic, it means no heat transfer. It's like throwing it into your cooler. Hopefully your cooler does not have any heat leaking out of it. So then that means that the heat transfer from the aluminum equals the heat absorbed by the water. And the heat transfer for both is mass times specific heat capacity times change in temperature. We don't know the final temperature, so we have to set them equal to each other. And the other thing is you have to put a negative sign on one of the sides, because that's just the direction of heat flow. I put the negative sign on the aluminum. The book put it on the water, but either way it's fine. Because I don't know why the book did it that way. Oh, it just says it's a relationship. Okay, the book says it's a relationship. I'm being a stickler. I'm saying the heat flow is negative because it's leaving the system for aluminum. But either way, put a negative sign on one side there, it doesn't mean anything. Okay, so then you can put the numbers in and solve for temperature, or you can do it all symbolically like I did and punch in the numbers, and you get 17.3 degrees Celsius. So questions on how this one works? On the final, there's not going to be a problem this hard. It's not a really hard problem, like I said, it's just a lot of steps. So it's just more chances for you to mess something up. One of the reasons why I go over this in a little more detail is that UH Manoa has a lab that they do this over and over again. And the students don't get as upset when they're having trouble. Well, the students have less trouble with their calculations. So, is this it? Oh, we have more on this one. Okay. Oh, I thought I was done. Okay. So questions with that? No. Okay. More thermodynamics. Yay. Okay. To inflate a balloon. So here now we're talking about pressure, volume, work. So we talked about how work works or how heat works with the first law. Now we're talking about work. So, and in this case, the expanding gas. If you know how your car works, most cars are gasoline. It would work the same idea with the diesel engine. The way your car works, you have a piston. So I have two cars. Well, I own one car. My wife owns the other. They're both V4, which means there's 4 cylinders in it. And maybe you heard of V6 and V8. That's just the number of cylinders. Okay, so the cylinder works. It's a piston. It goes up and down. Okay, so then the action of the piston going up and down will then turn basically a bar, and you have gears attached to that bar, and it transfers the mechanical energy to whatever it is you're running in your car. You have some that goes to your air conditioner if you have an air conditioner. Some goes to your alternator that recharges your battery, powers the car. And of course, most of the power goes to the wheels to have it go forward. And the way the piston goes up and down, there's a chamber, and when the piston goes down or goes up, your fuel injector will inject gasoline and air into the cylinder. Then there's a spark plug, and then that ignites the gasoline. So it's an internal combustion engine, inside combustion. It have an explosion, and the force of the gas expanding pushes the piston up. So that's how we transfer the energy from gasoline and convert it into work, is from the expanding gas, from the gasoline and the oxygen exploding in your engine and forcing the pistons up. And then by using gears, transferring that into moving your car forward. So one of the ways that a chemical reaction does work on the system, well, the primary way, is by expansion of a gas. And just like it takes work, right, to breathe in, so you can do work on a system that way. And the equation for work is negative pressure times the change in volume. And this also is under constant pressure. So if the pressure is changing, then you have to use a different equation. That's one of the assumptions for this equation. Because I'm looking at the equation now, it's external pressure. So like if you have a system where your pressure is ever changing, like a rocket going up into space, this equation won't work as well. Unless you're inside the rocket, and unless you're inside the pressurized container in the rocket, then you're fine, because your external pressure hopefully stays the same. But anyways, so under that circumstance, this works. Inflate a balloon, you have to do pressure volume work against the surroundings. You inflate a balloon from a volume of 0.1 liters to 1.85 liters against an external pressure of 1 atmosphere. How much work is done in joules? And part of this is the so direction, and And so we have our system. So the energy going into the system or out of the system, it depends on the direction. So and it also depends on your reference frame. So for the balloon, the balloon is expanding. So as the balloon is expanding, it's pushing on the surroundings. So the balloon is doing work on the surroundings. It's expanding. If you call me the system, I'm blowing up the balloon, I'm putting work into the balloon. So if in that case, my work is negative and then the balloon is positive. So this is one of the things, it's almost like relativity meets chemistry kind of thing. So relativity deals with, it's a theory of physics with Einstein. You probably heard of Einstein, how it depends on your reference frame. Same thing with whatever it is, with the first law. You have to pick your reference frame and then have the equations work, and at least in terms of the negative signs. So, okay, so our work, how much work is done in joules? Use this equation, work is minus P delta V. So our pressure is 1 atmosphere minus 1 atmosphere. Change in volume final, 1.85 liters minus 0.1 liters. So we get minus 1.75 liter atmospheres. And you're like, okay, what the heck is a liter atmosphere? So, liter atmosphere, well, what you can do is look at the two values of R, and you can, and we want it in joules, so we have minus 1.75 liter atmospheres times, I'm going to say 8.314 joules per mole Kelvin all over 0.08206 liter atmosphere mole Kelvin. I think that's 101.3 if I remember correctly. If you're given the 101.3, so the moles Kelvin cancels there. And then you see you have joules per liter atmosphere, so then the liter atmospheres cancel there. And like I said, I think it's 101.3. 8.314, because that's the same as pascals or kilopascals to atmospheres. 0.08206. Yeah, it's 101.3 times 1.75. So we're getting minus 177. Let me think we have 3. Yeah, we have 3 joules. And then you're like, what's the answer? Like I said, it depends on the context. So depending on what you're choosing your system as, if the user blowing up the balloon is a system, the work is negative, and in that reference frame, then the balloon is the positive work. If the system is the air, it's receiving work from the balloon, so then that's the negative direction. It really just depends. I think the book has it as positive. What the heck does the book say here for that? Oh, it has it as negative. Okay. Just says negative work. Doesn't really explain the system. Okay. So, and I'll go ahead and take a picture. What is everyone? Did my thrilling love of the topic scare everybody away? Okay, recap on this one, but again, this is pretty straightforward. We have equations here. Work is minus pressure, change in volume. Change is always final minus initial. So plug in the numbers, external pressure, 1 atmospheres, we get negative 1.75 liter atmospheres of work. What the heck is a liter atmosphere? You take the ratio of the values of R to get the conversion, and you get negative 177 joules. So, questions with this one? Have you seen the heat transfer energies? I mean, if you look at the amount of energy in things, I mean the amount of work that you do, like blowing up balloons or going up mountains and that kind of stuff. I remember I was climbing up a mountain one time. I was like trying to mentally calculate how much work I'm doing, and it's like, man, I'm not really gaining that much gravitational potential energy. How much I'm like sweating. I'm like sweating buckets. I'm like, man, I didn't really gain that much work, or gain that much potential energy. There's a huge amount in chemical reaction. There's much more energy in heat transfer. And chemical reactions, huge amount of potential energy. Even bigger than that is nuclear. So nuclear is, of course, is even larger. The potential energy in matter itself. So if you're wondering where things lie, and that's nothing. Also might explain why you get so hungry if you sit in the pool for a while, because all that, or the ocean, all that, as long as the ocean temperature is below 37 Celsius, you're losing energy. Okay. Questions so far with this one? All right. Oh, okay. Okay, the change of internal energy in a bomb calorimeter. Okay, so this is what I told you before about like when you see things. This is actually also a legal law. So the U.S. government recognizes the fact that thermodynamics works, and we have series of laws. I think I told you about this with the lab and whatnot. We have the Code of Federal Regulations, bunch of laws dealing with the codes, and there is a law saying how you can determine how many calories are in a food. So let's say you're working for someone and you create something new, like a new sweetener. So saccharin, Splenda, neotame. So neotame hasn't really hit the market yet. At least I haven't heard of too many things having neotame. But the idea with sweeteners, like artificial sweeteners, is that they're sweeter than sugar. So also certain sugars taste sweeter to us humans than others. So sucrose we is our baseline. Sucrose, that's the white sugar you buy in the grocery store, stuff that's in sugar canes. We run off of glucose. Glucose doesn't taste as sweet as sucrose. Fructose tastes even sweeter. So that's why we have enzymatic action. We have high fructose corn syrup because it tastes better than sucrose. So then if you ever grab packets of sugar versus packets of sweetener, the packets of sugar, they're really fat, right? So if you're going to put sugar in your coffee, they're really, really fat. And like the sweet and low and equal, sweet and low, that's saccharin, and the equal, that's usually aspartame. And I guess the yellow ones are Splenda. I don't like Splenda myself. But if you ever open them up and pour them in there, like there's a little tiny bit. I mean, like the sugar, they're pretty big and fat. But then they put their big crystals in there. And the artificial sweeteners are little tiny powders. And the idea is that we taste that as super sweet. So it's just tricking not really tricking, it's our chemical sensors on our tongue. So, but they have calories. So there are calories in artificial sweeteners, much less than sugar. But how do we determine the calories of that? Well, we burn it. And we use a bomb calorimeter. And maybe I should, there's a picture of one right here. I should have space here. Yeah, I should have done this before. Here is a bomb calorimeter. So you have whatever it is you want to study, and you have oxygen in here. There's pure oxygen going in here. and you have an ignition wire, and it burns the stuff in here. And you have, it's usually set in water, and this is very heavily insulated. And also, doing experiments, they can figure out the heat capacity for this very exactly. So then you burn whatever it is you're studying in this bomb calorimeter, and then that will then be used for the number of calories in something. That's a legal thing, but they do it for other things too, like you ever see the charts for like the delta E and whatnot for aluminum? We'll talk about standard states later. We did this for many other compounds other than the stuff that we're going to eat. Things like aluminum and titanium and iron to get the energies of reactions. So, all right, let's go ahead and do this. When 1.01 gram of sucrose is burned in a bomb calorimeter, temperature raises from 24.92 to 28.33. Find the change of internal energy for the reaction, the combustion of sucrose, in kilojoules per mole sucrose. The heat capacity for the bomb calorimeter is 4.9 kilojoules per degree Celsius. And ignore the heat capacity of sucrose because it's negligible. Okay, so I know that we've been doing this equation here. Heat, the bottom one, the heat is mass times specific heat capacity times change in temperature. But this has already been figured out, so we can just look at the heat capacity, the plain old heat capacity. And then the system idea. So if the system is the bomb calorimeter, the energy flow is positive because it's heating up. So we can know that because it goes from 24.92 to 28.33. So your bomb calorimeter is absorbing heat. If your system is a sucrose, it's losing energy. So energy is leaving the system. So this means that so I guess I can write this out. The Q calorimeter is positive. The delta E reaction is negative. I'm saying with the heat flow, the sucrose is losing energy as it's burning, and the calorimeter is gaining energy. So, and they're also equal to each other. The heat flow of the calorimeter equals minus the delta E reaction. Okay, so let's figure out the Q of the calorimeter. This is going to be the heat capacity times the change in temperature. Heat capacity is 4.9, and kilojoules per degree Celsius times the heat change, the temperature change. So it's always final minus initial, 28.33 minus 24.92 degrees Celsius. So degrees Celsius cancel. And I might cheat and just look at the book. And this equals 16.7 kilojoules. Okay, is everyone good up to here so far? Okay, so now we're going to apply this relationship and the delta E reaction, and this, I should also say this is per gram, and this is for 1.01 grams of sucrose. Delta E reaction equals negative 16.7 kilojoules per 1.01 grams of sucrose. Sucrose, do they tell you what sucrose is? Oh, right there, yeah, it does. Okay, then we have 342 grams of sucrose per mole of sucrose. I have that memorized. What is it exactly? It's 342.3. Not close enough. So equals 16.7 times 342 divided by 1.01. And we get 5655 kilojoules per mole. And I know a kilojoule, so if you look at this, the kilojoule, of course, kilojoules means 1,000 joules. But typically, chemistry, it's kind of, oh, I forgot the negative sign. It's considered bad form to put things in megajoules. So usually you put it in kilojoules. And what's commonly used then is we do 5.66 times 10 to the third, so negative sign, kilojoules per mole. And it's just to, and it's just to keep the kilojoules per mole here, and then out of there. I know it's kind of weird, bad form. Where are the 3 sig figs from? This book has it down to 3 sig figs. Oh, the delta, the heat capacity has 3 sig figs. Okay, so that's why we're doing 3 sig figs. Okay. All right. So, all right then, recap. We have our bomb calorimeter, and in this bomb calorimeter, we burn some sucrose, good old sugar. And the temperature of the water increases, the temperature inside the bomb calorimeter increases, and we know the heat capacity of the bomb calorimeter, and we know the mass of the sucrose, and we want to figure out what the change in internal energy for this combustion of sucrose is. So we calculate the heat flow into the bomb calorimeter to be 16.7 kilojoules for 1.01 grams of sucrose. Then by dimensional analysis, we get that to be negative 5,655 kilojoules of heat per mole sucrose. And then we convert it then further to minus 5.66, negative 5.66 times 10 to the third kilojoules per mole. So, questions here? Are you following? All right. So, another thing I forgot to mention last class, you can see, like for me, I have the heat capacity of water memorized. I don't have anything else memorized. That's the only heat capacity I memorize. So you have to look things up frequently. And it's nice and easy in this textbook, right? And if I have to look up a heat capacity, I frequently do it by looking at Wikipedia. Bad habit, yeah, I know. But and sometimes the units are kind of weird. So frequently you have to do something to convert the units. So you can get units in heat capacity. Sometimes it's kilojoules per kilogram. So for instance, like let's search around for some units. Okay. Siri, what's the heat capacity of aluminum?
Here's what I found on the web. What's the capacity of aluminum?
Okay. We'll look at the table. There's got to be something interesting here. Oh, it's joules per gram degree Celsius. That's nice. Sometimes they're in weird units though, so let's. Oops. Let me look at my periodic table. They might have heat capacity. Let's look at gold. Okay. Does it give? Doesn't give the heat capacity. Wolfram alpha. Boiling point. Thermal conductivity is like heat capacity. Noise hardness, speed of sound. Half-life. Oh, it doesn't have the heat capacity in there, does it? There's a thermal conductivity, but no heat capacity. Oh. All right. Can I see the Wikipedia page for aluminum?
I don't see anything about that on Wikipedia.
There's nothing on Wikipedia about aluminum. I don't believe that. Oh, well. My point is, sometimes when you look at things, you'll find units. Sometimes they'll be in moles. Sometimes it'll be in grams. Sometimes it'll be kilograms. You can use dimensional analysis to get the units that you want. The other thing is you'll sometimes see the units as in per Kelvin. Like if you look at water, like wait a second, so you might see water as 4.18 joules per gram Kelvin. And I have also said this is the same thing as 4.18 joules per gram degrees Celsius. So unit-wise, a Kelvin equals a degree Celsius. So if you look at a change in temperature, a change in degrees Celsius is the same change in kelvins. And if you divide by Celsius or multiply by Celsius, it's the same thing as multiplying or dividing by Kelvin. So those unit-wise are indistinguishable. So multiplication and division and addition and subtraction. Assuming that each is in the same state, right? So if you, of course, if you say 0 degrees Celsius minus 298 Kelvin, then you're going to get the wrong answer. You have to convert one to the other. Because so the magnitude is different for Celsius and Kelvin, but the units, the step, a 1 step Celsius is equal to a 1 step Kelvin. So if you have a change of one or the other, it'll be the same. Or if you look at a multiplication division, the units will cancel. So keep that in mind if you're looking stuff up. Anyways, questions so far? All right. "18 grams of glucose burns in a bomb calorimeter. 1 kilogram of water in the calorimeter raises from 10 degrees Celsius to 70 degrees Celsius, and assuming that's thermally isolated. The heat capacity, specific heat capacity for water is 4.18 joules per gram degree Celsius. What is the delta E reaction for burning of glucose?" And I'll go ahead and give you a hint. This is 180 grams per mole, and Q is mass times specific heat capacity times change in temperature. Okay. Oh, it's your table. That's like a big bird trying to talk to me or something like that from Sesame Street. Is anyone completely stuck, has no idea what to do? Okay. So how many think it's A? How many think it's B? How many think it's C? How many think it's D? Okay, so a couple people going for B. When you eat sugar, do you get energy from eating sugar, or does it suck energy out of you and you you actually lose energy. So like a way to lose weight is to eat a bunch of sugar because your body's gonna have to burn all your fat to take up for the energy that's being absorbed by the burning of the sugar. Heat flow is negative. So combustion of sugar is very energetic. So it's not, B and D are wrong. So think of direction. Okay, so we have two people going for B, but no one else wants to play. But I'm going to come around and I'll see what the guys are thinking. Okay. How are you doing this week? It's great. Oh, you want more? Okay, here I'll. Can you read that? Yeah. Okay, maybe that'll help. Let's. It's that's the sugar. It's what flavoring water. So use 1,000 grams there. And it's also, I just remember keeping kids in around because it's going to be 2,500,000 Yes, that's right. Because the water, yeah, you will convert it to because like you see above here. Yeah, that's like after you figure you have something that's in joules, and then you just divide by well, what's reacting? Okay. So two forms of the equation. There's the heat capacity times changing temperature, and there's heat is also mass times. So specific heat capacity. This is the density. I like this. What's the weight of water?
kilograms. Or you can say, well, I have 10 liters of water, the density of water is 1 kilogram per liter, and then so you're doing the same thing. Yeah. Right? It's just this term becomes that term. And which ones do you know? Well, they tell you the heat capacity, they'll say heat capacity, this will say specific heat capacity. So, and okay, the thing is you have 18 grams, that's for the sugar. Using water.
Oh, the water.
Yeah, that's 1,000 grams. That's right. It's going to be 2,500. And then that's joules. And that's for 18 grams of water. I'm sorry, 18 grams. 18 grams of water. And then 18 grams of glucose, so glucose is 100 grams per mole. So and the other thing is it's a negative direction. Because sugar. If you look at the sugar, the energy is leaving the sugar. It gives you energy, doesn't give you energy.
All right, it looks like everyone's converging, and the answer is A. The most common mistake I saw is that people were putting 18 grams here. So first of all, 4.18 joules per gram degree Celsius is not the heat capacity for glucose. That's heat capacity for water. But the water is what's absorbing the energy. And the other question I got is, how do I know when to use the right which equation? When do I use the top equation? When do I use the bottom one? You have to look at the problem. So if it says heat capacity, use the top one. If it says specific heat capacity and then a mass of something is given, use the bottom one. Okay, does that make sense? Questions, anyone? All right. So here's my not as good as Banksby. You ever see that the girl with the balloon that just got shredded when it was bought? You don't know that? Banksby, he's a graffiti artist, the popular one. Here is my attempt at art and science. You should take a class with Peter Fisher. He's actually a proper artist. So exoskeletons, kind of like insects have exoskeletons. It's like armor. They have their skeletons on the outside. We humans, we have endoskeletons. We have our skeletons on the inside. And so just the idea, this is supposed to be a flame. Exothermic, just like the exoskeletons on the outside, energy leaves the system for exothermic, and this is a snowman if you don't know what this is. This is endothermic, heat goes into the system there, and endothermic means the heat is in the positive direction. So, I've already said that, but here's that. Okay. All right, so we've learned about internal energy. Now I'm going to talk about a different term. A term is called enthalpy. So enthalpy. Also known as H. Enthalpy is the combination of the terms. Enthalpy is energy plus pressure times volume. So, and under constant pressure, this is actually, has anyone taken Calc 1? Have you done the multiplication rule for derivatives yet? Are you there yet? Okay. So if you have pressure times volume and you take the derivative, this is going to equal to pressure prime times volume plus, pressure volume prime. You've probably seen that before. So this is saying constant pressure. So the constant pressure, this term goes away. And so then you get, so if you take the derivative of this, so if you take a derivative of that, you're going to get, this is going to be E prime plus P prime V plus PV prime. And constant pressure gets rid of that term, and you're left with this. So there's your calculus. So, although this class does not require calculus, but there's calculus in chemistry. Okay, so delta H is delta E plus P delta V. And delta E is work plus heat, that's the first law. And P delta V, we've learned before, that's minus work. So that means then that at constant pressure, the enthalpy delta H is equal to the heat transfer. And the delta H many times is referred to as the heat of reaction. And also another side topic, thrust. Thrust is also equal to delta H. So if you wonder what's keeping the airplanes up, what shoots rockets into space, it's the enthalpy of the chemical reaction. So in case of, well, some rockets use kerosene. Airplanes usually run off of kerosene. The Saturn V rocket ran off of kerosene. But, okay, so enthalpy. So the value of delta H is the heat absorbed or evolved under conditions of constant pressure. And for here on Earth, basically use delta H, unless you're changing your pressure, right? So unless you're studying a chemical reaction on the surface of a submarine as it's dropping down the ocean, or a chemical reaction happening on a rocket as it's shooting up into space, you're not going to have to worry about a change in pressure. If you do that, using the multiplication rule of the derivative of calculus, you can figure out how to do it, right? So you can do it. But here on Earth, most everything is at a constant pressure. Okay, and endothermic reactions and processes feel cold. So Ice melting is an endothermic process. It feels cold when you touch ice. Exothermic feels hot. So if you stick your hand into burning embers, I don't recommend you do that. It feels hot. Although I've done it accidentally. So exothermic reactions feel warm to the touch. So surprise, surprise. Okay. And we will learn more about, we still have time, where's B? We still have time for enthalpy. Oh yeah, we have 15 minutes, okay. How are we doing? Anybody have any questions with enthalpy? No. Okay, don't worry, there'll be more. There'll be time for questions. But enthalpy, H is just E plus pressure volume. And you'll see this a lot in thermo. This will probably not be the first class you have that talks about thermo. You'll probably have classes that talk about thermo in great deal. There's also a term called Gibbs free energy, which is enthalpy minus temperature times entropy. So this is not the first time you're going to see this other term defined by another term, other combinations term. So a liquid propane gas tank and a home barbecue, this is making me hungry, contains 13.2 kilograms of propane. Calculate the heat in joules associated with the complete combustion of the propane in the tank by this equation here that has 2044 kilojoules of heat. Okay, so when you look at this equation here, the other thing with stoichiometry and energy, when you see a delta H or delta E or delta G, delta S, it's always per mole reaction. So it's nice because propane here, it's a 1 to, it's a 1 here, so it's going to be, you're looking at propane, it's exactly that. If we're looking at oxygen, it would be a 5 moles oxygen to 1 mole reaction, if that makes sense, because that's the whole mole reaction thing. And the other thing, you'll frequently see things as listed as per mole. That's also implied mole of the whole chemical reaction. And that is just the end. The delta H is considered a 1. So this would be a 5 to 1, 3 to 1, 4 to 1, and propane a 1 to 1. So you include the stoichiometry stuff in that. Okay. But it's a 1-to-1 reaction, so it's fine. So look at propane tank. Calculate the heat in joules. Okay, 13.2 kilograms of propane, C3H8. So then that would be 1,000 grams per kilogram. And it's propane. I don't want to write propane. Okay, C3H8, so 3 times 12 plus 8. 3 times 12, that's 36, plus 8, that's 44. Also the same as carbon dioxide. 44, oh, I got it on the wrong side. 44 grams of C3H8. 2 moles C3H8, is that right? So 36, yeah, that's right. 36 plus 8, that is in fact 44. Okay. And then we have 2044 kilojoules per mole C3H8. If you want, you can put another step in there. I could put mole reaction, and then it's a 1 mole reaction to mole C3H8. You want to do it that way, but like I said before, it's already a 1-to-1 mole ratio, so you don't have to worry about that step. Okay, so doing this calculation, 200 by 44 times 0.44 So this equals 6.13200 kilojoules. How many sig figs? We have 3. 6.13 times 10 to the 5 kilojoules of heat, and where's my cell phone? There it is. So in the sign, however you want to interpret the sign, if you want to say how much heat is evolved, is how much heat is associated with the complete. Since it says heat is associated, I should probably put a negative sign because that's say it's leaving the system. But again, the direction there, and like I hope you're also following my logic. At the end, this is when I go through and I'm like, all right, where's my heat go? Where's my energy going? Where's it flowing? Am I going in the right direction? Kind of thing. So that's when I come back and I use my intuitive side to try and figure out where the heat flow is and make sure I didn't mess up a negative sign somewhere. Okay, but this one here, it's just plain old dimensional analysis. So, and the difference though is that we're including the stoichiometry of the chemical reaction in with this. In this case, one mole of propane makes this much heat. And we're converting 13.2 kilograms of propane to that much heat. That's a lot of heat, right? That's 613 million kilojoules. So that's a million. That's 6 billion joules. That's a lot of energy, right? You think about that. I mean, we're talking about picking up pennies in the snow, and that's like 50 joules. Remember, that's a penny. That's 50 joules, and then this is 6 billion joules. That's a lot of heat, right? So you think pennies feel cold. I guess you don't know what a penny feels like in the snow. Maybe some of you do. Right, so a lot of energy and fuel. Kind of wish we could have a barbecue right now. All right, and then, I'll say, this is pretty straightforward. Does anybody have any questions with this, how this works? You look amused, Will? Or, no? Okay. Sorry if I'm calling you out. Just smiling. That's cool. All right. Next problem. Magnesium reacts with hydrochloric acid by this equation. An experiment determined the enthalpy change to this reaction. 1.58 grams of magnesium metal combined with the excess hydrochloric acid and to make 100 milliliters of solution. The solution is sufficiently concentrated that the magnesium completely reacts. Temperature rises from 25.6 to 32.8. What is the delta H? The reaction as written. Use 1 gram per milliliter as a density of solution. Heat capacity solution is 4.18. So from the previous talk, right, so using this, we know that we're going to use the Q as M CS delta T because you're given the specific heat capacity, and then you're also given a density, and it's 100 milliliters. So our mass is 100 milliliters times 1 gram per milliliter. So it's 100 grams. So, and then, so the mass, we're gonna have the mass be 100 grams, specific heat capacity 4.18 joules per gram degree Celsius. Change in temperature, final minus initial, minus 25.6 degrees Celsius. Right, so, but I guess I should back up. I had a student in my office hour yesterday trying to figure out how to do, she said she hated word problems. Okay, so the way that you do this, and oh, I just realized I told you I was going to give your test back, and I forgot to bring my test. Shoot, sorry about that. I'll give them to you on Monday. Anyways, so this here, you're looking for the delta. This is the delta H reaction. We're looking for the delta H reaction, and similar, we're going to look like the bomb calorimeters. We're going to look at the heat flow. So we do the reaction inside a beaker, and we're going to get the heat flow from that, and then gives you the mass of the magnesium. Okay, 0.158. And this is also a limiting reagent problem, but we have an excess. So the HCl is said to be an excess. So it's a that. So how do you figure this out? You look at the given information. So you think, okay, limiting reagent problem. Magnesium is our limiting reagent because it tells us that. So the energy from the reaction is going to be from the magnesium going to completion. And then since you were given a heat capacity and a volume and a density, you know you have to use this equation. And then we get our heat flow, and from our previous, I went home. Recognize my fingerprint too much that time. Okay, but so let me calculate this out, times 4.18 times 32.8 minus 25.6. So, got 3 minutes. 3009.6 joules, and this is per 1.158 grams of magnesium. So if we want our delta H reaction, this is going to be equal to minus 3009.6 joules per 0.158 grams magnesium times, I think it's 24.3. Is that what magnesium is? Magnesium is 24.3. Okay. 24.3 grams magnesium per mole magnesium. So I just take that and multiply it. 24.3 divided by 0.158. And in doing so, we get minus 4.62869. So that means this equals minus 462 kilojoules per mole. Okay. Was it? All right. This has a 3 sig. This has a 2 sig figs. Huh. The book is wrong. Oh well. All right. So, just like the heat flow, the water is increasing in temperature, which means that it's absorbing heat from the chemical reaction. That means the chemical reaction is exothermic, and the heat flow from the reaction's point of view is negative. And I've already gone over how you solve this equation. So we put in this equation to figure out the heat flow, and the heat flow is for 0.158 grams of magnesium. Converting to moles, we get 400,000 joules. So minus 400,000 joules there gives you the answer. Questions with this? All right, class is over. I will see you on Monday.